Welcome to the Problemers Channel Season 3, Episode 17, the episode which I titled 4-Point Square Reconstruction, because in this episode we will look at 4, not at 5, as I promised at the end of the previous episode, but actually at 4 distinct solutions of this problem, because upon a closer analysis, my 5th solution turned out to be not a solution after all. So 4 distinct solutions of the problem of 4-point square reconstruction. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence, and thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the homepage of this channel, and at the top of that page, in the channel's trailer section, find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, by all means do ask. The best way to ask your question is to find an episode that is of interest to you. Use the comment section under that episode to ask your question, and I will do my best in order to answer all of your questions. And of course, also as usual, I would like to extend my gratitude to all the current subscribers and the current supporters of our channel. Our current challenge is the mathematical problem S3E17, and back in the day when I as a kid was growing up in the 1970s and 1980s Moscow, then USSR, through the word of mouth, or as the overall mathematical folklore or mathematical folk tales, if you will, this problem was known to us as the Sofya Kovalevskaya problem. And whether that is true or not, I honestly do not know. I'm not making any claims. Take it for what it's worth. But the idea in this problem is the following. The mathematical oracle, or if you do not like the mathematical oracle, a math professor walks into an empty class, picks up a piece of chalk, and on the board, the professor draws the square PQRS. Then on each side of the drawn square, the professor picks at random one point in such a way that every such point is distinct from the corresponding vertices of the parent square. For example, the professor picks a point A on the side QR of the parent square in such a way that the location of the point A is on that side random, but the point A is distinct from the points Q and R. Then the professor picks the point B on the side QP in such a way that the location of the point B on the side QP is completely at random, but the point B is distinct from the points Q and P. Then the professor does the same thing for the point C and the same thing for the point D. The point C is picked at random on the side PS in such a way that the location of that point would be anywhere on that side, but distinct from the points P and S, and the point D is distinct from the vertices R and S of the parent square, but the location of the point D on that side RS is random. Then professor takes a piece of cloth and erases the square, but keeps the 4 points A, B, C, D chosen at random, 1 point per side. And now he lets the students in. The students walk in. The students right now are looking at the 4 points A, B, C, D. And the objective of this problem is to, as the title of this episode suggests, reconstruct the parent square PQRS given such 4 points A, B, C, D using ETO, Euclidean tools only, meaning using a compass and a straight edge. And the idea here, of course, the reconstruction means an algorithm that reproduces the square that was erased PQRS with absolute certainty and correctly. The problem that we're about to solve not only lives on the great international mathematical grape wine, but this is also an amazing problem, and by now all of our viewers should remember that a problem in mathematics is an amazing problem if and only if every time we look at that problem, we come up with yet another solution that is distinct from all the previously generated solutions. One of the most perhaps famous and publicly known amazing problems in mathematics is the problem of proving that the square constructed on the hypotenuse of a right triangle is equal to the sum of squares constructed on the sides of that triangle, otherwise known as the Pythagorean theorem. And as far as I'm aware, about 300 distinct enough proofs of that theorem are known by now and have been cataloged. So here the solution number 1 of this problem is based on the following orthogonal intersecting chords theorem, and as all things in hard sciences, the name of this theorem is somewhat pretentious and sounds very scary, which it is not. And the gist of this problem is the following. Let's say that we agree that for the duration of this problem, we will call a chord of a square is precisely a line segment that connects to opposite sides of a given square. And for the purposes of this theorem, we can even admit or allow the points that this line segment connects, the chord connect the diametrically opposite vertices of the square. But in general, for us, let us say we will lay that proof of that theorem right on top of what we are given. Let's say we take a point A and the point C, and we make our first assumption that the points A and C belong to the opposite sides of the square. That is the first assumption, and we'll come back to it in a few seconds, and you will see why that assumption is substantial. As such, assuming for a moment that the points A and C belong to the opposite sides of a square, again, we take the points A and C to be picked at random, we connect them with a line segment, we call that line segment a chord, and now we pick another point on a side of the square that did not participate in the formation of the chord AC. We can pick the point B, we can pick the point D, it doesn't really matter. For demonstration purposes, we will pick a point B. And through that point B, we will construct a perpendicular straight line. We will refer to this straight line as, let's say, lowercase pb, that is perpendicular to the given chord AC. And let us assume that that perpendicular straight line intersects the opposite with respect to the side where the point B resides, side of the parent square, at the point E. In other words, BE is yet another chord of the given square. And what we have here is two intersecting orthogonal chords, AC and BE. We can even record that AC is perpendicular to BE, or orthogonal, if you will. So now the theorem that we're about to prove claims that if we take in any two random chords in a square that intersect in an orthogonal fashion, then the lengths of these chords are exactly the same. In other words, the length of the line segment AC is equal to the length of the line segment BE, and the proof of that theorem is less than trivial. Here we do the following two steps. We project the point A orthogonally onto the opposite side into the point X in such a way that the angle AXC is right. And we do the same with the point B. We take the point B and we project it orthogonally onto the opposite side of the parent square into the point Y in such a way that the angle BYE, for example, is right. The corresponding triangles AXC and BYE are right. And we're about to prove that these triangles are congruent by what? Angle, side, angle. And we do that as follows. Our projections AX and BY will also evidently intersect the chord BE over here, at the point E. In other words, BE intersects AX at the point O. And now we consider two smaller right triangles. The triangle formed by the points A, K, O, where K is the point where, let's say, which sides AC intersects BE over the point K, and AX intersects BY over the point L. This is the point right here, and we consider two smaller right triangles, AKO and BLO. In these triangles, the interior angles at the vertex E, which is shared, are vertical and hence are equal by magnitude. The interior angles at the vertex K and at the vertex L in these triangles are right. The magnitude of the interior angles in any planar non-degenerate Euclidean triangle sum to pi. That means that the magnitudes of the remaining angles must be the same. The angle alpha in the smaller triangle AKO and the angle alpha in the smaller triangle OLB, for example. They must match, but these angles marked as alpha also play the role of the interior angles in the larger right triangles, the triangle AXC and the triangle BYE. And that means that in, let's say, in the shape AX, what did we have here? We have PQ. So the shape AXPQ is at the minimum a parallelogram, because our side AX is parallel to the side PQ of the parent square, and in all parallelogrammatic areas, the length of the opposite sides equal one another. That means that the length of the side AX is the same as the length of the side PQ. Let's designate it with A, lowercase a, the side length of our parent square. And in the area PQ, that was our vertex R. This is vertex S. In the shape BYSP, what is the shape? This shape is also at the minimum a parallelogram. We can make a stronger statement. We can prove that this is a rectangle, but in all parallelogrammatic areas, the lengths of the opposite sides are equal one another. That means that the length of the line segment or of the side BY is the same as the length, which one? SP, but that is also the side of the square A. And that means that AX, the length of the line segment AX, is equal to the length of the side BY. And there you go. From the angle, side angle principle, it follows, congruence principle, it follows that our triangles, the triangle AXC is congruent to the triangle, which one? BYE. And then congruent triangles against angles of equal measure lie sides of the same length. So against the right angle in the vertex at the vertex X and the triangle AXC, there lies the side AC, and against the equal magnitude angle at the vertex E, there lies the side BY of this triangle. And this precisely means, from this it follows that the length of the side AC is equal to the length of the side B. This is exactly what was required to prove. We will put the end of proof signal, end of proof marker over here. The theorem is proved. If you have any questions, the comment section is open. And now, once we prove that, what is the first algorithm that comes to mind? Well, the first algorithm that comes to mind is the following. Let's say we, again, assuming that the points A and C live on the opposite sides of a mystery square. As a first step, we connect the line segment AC. Then we can always do it with a straight edge. In some sense, this is what the this theoretical tool known as a straight edge. That's what it was born for. Put a straight edge across the points A and C, snap a line, we have it. And then let's say we have choices, of course. We can do it with the point D, we can do it with the point B. For demonstration purposes, I'll pick the point B. Through the point B, we construct a perpendicular straight line to AC through the point B. That also can be done with a straight edge and a compass. And now that we have this straight line called PB, what do? We take our favorite compass, and then we open up that compass. To which distance? We open up that constant compass to the distance. Apparently, that's even, this distance is bigger than what I can show, but you understand. And then at the point, we use the point B as the center, and we draw this circle of the radius AC starting from the point B, and that circle will intersect the perpendicular PB, the straight line PB, actually at two distinct points, and one such point will be E. The other point will be way above my board. I will not be able to show it, but we will talk about that point in a second. But now that you understand the idea, the line segments A, C, and BE are equal, and that means that if it so happens that the point D is distinct from the point E, then two distinct points define a unique straight line. And once we have that point cut off by the circle that is constructed as I explained, then boom, we have the solution of our problem. We snap the straight line DE through the point A. We snap a straight line perpendicular to DE. Through the point C, we snap a straight line that's perpendicular to DE. Once we have these two straight lines, through the point B, we snap another perpendicular to either that side or that side, and the game is over. Now I will take a second to erase the board and put together the first algorithm that solves this problem with Euclidean tools only, with absolute certainty and correctly. Given the four distinct points A, B, C, and D according to the solution 1 in our algorithm, as a first step, we draw the straight line through the points A and C, assuming that the points A and C belong to the opposite sides of the square. That straight line AC is shown in white over here. And the second step, we draw the straight line called PB, orthogonal to the line segment AC through the point B, orthogonal to AC through the point B. That straight line is shown over here. I only show the portion that really fits on my board, but that straight line runs evidently all the way to the other side. And as the step number 3, this is the key observation. We construct the circle S that has the point B as its center and the length of the line segment AC as the radius. In other words, we open up the compass to the distance between the points A and C, and using Euclid's Elements Book 1 Proposition 2, the Euclidean compass has memory. Without closing it, we can keep it and move, for example, the needle that was in the point A into the point B, snap a circle S, and that circle S will intersect the perpendicular bisector PB constructed in the step number 2 over two distinct and diametrically opposite points called E and E prime. E and E prime, and here across these 2 points we choose for the first solution the point E shown over here in blue that is on the same side as the given points. In this particular configuration, it will be closer to the point D than the other point E prime that sits above the boards. And once we have the point E, again assuming that the point D is distinct from the point E, we snap a unique straight line through the points E and D, and if it so happens that the points D and E coincide, this is one and the same point, then the number of solutions of this problem becomes not interesting, because there will be uncountably infinitely many such squares. So for now, we consider the interesting case when the number of solutions is finite, and all these solutions can be enumerated as such, assuming that the point D is distinct from the point E. We snap a straight line ED, and after that the game is over. As the fifth step, we know that the points A and C are on the opposite sides of the parent or mystery square, and we have the straight line ED that will house the corresponding side of the mystery square. And we do what? We snap a straight line LA perpendicular to the line ED through the point A. This is this blue line shown over here, LA perpendicular to AD through A. Next, we have our point C. So as a sixth step, we snap a straight line LC perpendicular to the same straight line ED through the point C. That straight line is shown over here, perpendicular, perpendicular, LC perpendicular to ED through C. This line, once we have these two straight lines, the straight line through B, this will be the final step, LB perpendicular to LA or LC, it doesn't matter, but through the point B, and the shape that will be delineated by the intersection of these four straight lines, ED, LA, LC, and LB, will precisely recover the square. The vertices will be here, P, Q, R, S. And the thing is, if we go back to our solution one constructive algorithm, we will notice that the key observation is that the solution circle, in some sense S, will intersect our perpendicular PB actually at 2. This is the straight line PB, lowercase pb. This solution circle S will intersect the perpendicular PD at two distinct and diametrically opposite points, and unfortunately, most of the time, most students completely fail to analyze what will happen if we consider the point E prime, and that point E prime will give the birth to the second and usually distinct from the first solution square nonetheless, but that square will be very interesting because not all the points will be precisely on the sides of that square, but some of these points may be located on the extensions of these sides. And here is the situation with the second point E prime. In order to make the point E prime visible, I had to scale down things a lot on my blackboard, but you do not have to using your favorite graphing software. You should really see that our solution circle S, that has the point B as its center and the length of the line segment AC as its radius, intersects our perpendicular PB through B to AC at two distinct points, E and E prime. And once we unwind the solution for the point that we call E, I hope that all the mathematically inclined thinkers in our audience will say, Roman, we wipe out this E and we keep the algebraic structure of our solution one algorithm exactly the same. We'll lose the prime over here, and now we make the point E prime, or the point formerly known as E prime, play the role of our formerly known point E, and pretty much keep the steps of the algebraic description of our algorithm verbatim. So the only thing we do over here is we do a slight adjustment in the geometry of the solution. Or we can also do here the following. We can keep the point E as it was, we can keep the point E prime as it is, but then we roll through our algorithm uniformly, and we prime every below this point over here, below this point for our second solution square. We prime every occurrence of the point E. What used to be E now becomes E prime, and if we do that and we carry out the corresponding construction, then we will see the following. And in order to help you visualize how these things work out, in some sense this is not really anything complicated. It's essentially, like I said, as the algebraic structure of our algorithm, it remains the same. We snap the same straight lines perpendicular to the same our solution straight line ED, except that this time the straight line, for example, E prime D, E, this is technically, we'll put E prime, our straight line E prime D will not be a side, or may not be a side of the square, but it will be a straight line that is extension of one of the sides of the second solution square. And in order to help you visualize how these things work, in a second you will see not exactly an animation but a demonstration where I put together the corresponding construction in the free software called GeoGebra. And in a few seconds, you will see that I will wiggle all the points. I will wiggle the point A, I will wiggle the point B, the point C, and the point D. And you will see how the second solution square that may feel a little funky at first behaves. Please take a look. Now that you saw my demonstration where I wiggle with the mouse the points A, B, C, and D, and the orange, you hopefully saw the behavior of the orange second solution square. You understand what is going on, but fundamentally, like I said before, we keep the algebraic structure of our first solution algorithm exactly the same, and the only thing that we do differently from our previous solution is the slight adjustment in the geometry, because we still draw the straight line E prime D, this straight line E prime D. For you guys to see this better, I drew that straight line with yellow chalk. This is the straight line. We connect the point E prime and D, see? But then again, we keep the same steps as we did in the previous algorithm. The straight line LA passes through the point A perpendicular to that yellow straight line E prime D. This is the straight line right here, LA. Now LC, because C sits on the opposite sides, or in this case, it belongs to the extension of the opposite side on which our first point A sits. We snap a straight line LC. It's shown over here, again, perpendicular to the yellow straight line E prime D through the point C. And now once we have these two straight lines, then we snap another straight line. This is called AB, which is perpendicular, for example, to LA. Of course, I draw everything by hand over here. You guys, when you will be doing it with the graphing software, everything will come out pristine. But the idea is that the straight line LB perpendicular to either LA or LC through the point B right here, in the intersection of these four straight lines, E prime D, LA, LC, LB constructed as explained, then they will trap inside a smaller square. This time, I apologize, the square is quite small, but this is the square that came out to be the second distinct solution square in my case, because I have constraints with the board. Just to make everything fit, I had to come up with this scaled down design, and you should really see how this second solution square is constructed. So now this is exactly the point where, unfortunately, most students to fail to make these observations most of the time. What do we have here algebraically? Algebraically, we have here is the following. From one assumption that the point A and the point C belong to the opposite sides of the square, we have how many solutions in general? In general, of course, under all the favorable circumstances, and I will talk about why I do not analyze to death all the possible mutual juxtaposition of these points, but from one assumption that the points A and C belong to the opposite sides of the square, we in general have two distinct solutions, two distinct circles. But if we fix the point A as our, let's say, fixed point, which we pair up with the points that live on the opposite sides, how many such pairs do we have? Well, first pair we picked, A and C on the opposite side. What is the second pair? The second pair is A and B on the other sides. And what's the third pair? The third pair is A and D that live on the opposite sides. And for each such pair, we know that again, in general, we will generate two solution squares. So again, in most general case, under all favorable circumstances, how many solutions we will have? Actually, yes, it's not one square, but as a mathematical inclined thinker, you should be able to make these observations that 3 times 2 comes out to 6. 6, in general, distinct solution squares will be generated by 4 distinct points A, B, C, D. But of course, if we take it that these points do not sit precisely on the sides of a square, but some of these points may be located on the extended straight lines that contain the corresponding sides. And for demonstration purposes, again, here I will show you a construction when, let's say, we assume that the points A and B, for example, belong to the opposite sides of a mystery square. As such, making an assumption that the points this time A and B belong to the opposite sides of a mystery square or to the straight lines that contain the extensions of these sides of the square, then we will have essentially the same construction as we did before. I kept for your reference the original algorithm on the right hand side of the board. You can compare it, but here we basically, instead of the point C, we take the point B to play the role of the point C. So in some sense, C becomes B, becomes B becomes C, C becomes B, and what do we have? Well, we connect the straight line AB, connect the straight line, this will be the first straight line AB. Then again, we have choices. We can do it through the point C or we can do it through the point D. For demonstration purposes, I pick the point D. Through the point D, we construct a perpendicular PD, that is straight line perpendicular to AB, through the point D. PD perpendicular to AB through D, and the game is over. We take our favorite compass, we open up that compass to the distance between the points A and B, but now we put that compass, the needle of the compass, into the point D, and we snap a circle. That has the point D as its center and AB as its radius. You see, like this. So that circle will intersect the perpendicular bisector PD at two distinct points. I called it E and E prime. I will not go into the discussion of the solution square that comes out from the analysis of, or from the work that follows, if we take the point E prime intersecting our perpendicular bisector PD. I will concentrate on the point E, but here, once we have that point E, we snap the straight line EC. I showed it in yellow so you guys can see it. So far so good. So let's say we number it. AB1 perpendicular, step number 2, the circle, step number 3, and this straight line CE is number 4, and in some sense game over, because now the straight line CE will contain one side of the mystery square, solution square, that contains, look at this time the extension of that side of that square, which I cross-hatched in blue, contains the point C. From our assumption that the points A and B belong to the opposite sides or to the straight lines that contain the extensions of these sides, what do? Well, we go back to our 4, 5, 6 steps. We snap a straight line LA perpendicular to, this time, to CE. Here it is in blue. LA perpendicular to CE through A. Then here LB perpendicular to CE through B. It is this straight line right here. All these steps can be carried out with Euclidean tools alone. If you have any questions, ask, but this is a trivial task of constructing a perpendicular to a given straight line through a point that is not on the given straight line. This can be done. And once we have these two sides of the mystery square recovered, the last one is the perpendicular through D to either LB or LA. Game over, problem solved. So now we have yet another square that is constructed on the assumption that this time the points A and B lie on the either opposite sides or the extensions of the opposite sides. And again, in order to make this situation more visualizable, more tangible, I put together a small demonstration. Again, in a few seconds, you will see I will wiggle the points A, whereas points A, B, C, and D in turn. And as I wiggle them, you should be able to see the behavior of the square that is shown on the board in blue, but in the animation, it should be in dark orange. Now that you saw my demonstration how the other square, solution square, behaves if we assume that the points A and B belong to the opposite sides or the extensions of opposite sides, again, you should see that if we take the point E prime to play the role of the point E, then in a similar fashion, we will construct yet another square, so another two solution squares, and by now you should really feel that from the third assumption that the points A and D lie on the opposite sides or the extensions thereof, we will have what? Like I said before, 3 times 2 equals to 6. So 6 in general, in most general case, 6 distinct solution squares given 4 points in the most favorable solution. And here is why. I do not want to, in this episode, torture and analyze to death all the possible mutual juxtapositions of these 4 points. Because if we decide to do that, then we will take on a task of its own completely separately. This is another rabbit hole that we have to dig, because that path in our analysis of this problem will lead actually to the answer to the following question. When do 4 points that belong to one and the same plane admit the construction of a finite number of squares? Like I said, this is a separate task. This is not the objective of this episode. The objective of this episode is to take one mathematical problem that I claim is an amazing problem and to construct as many distinct solutions of it as possible. Here we're done with the solution 1, and now we will move on to the solution number 2. The second solution of the mathematical problem S3E17 is in some sense more obvious or lies closer to the surface than the previous one. In the previous solution, we had to have a certain amount of mathematical perspicacity to see that the orthogonal chords that intersect under right angles in a square have the same length. It requires a little bit of knowledge and, let's say, mathematical maturity. But here, precisely because the interior angles, all interior angles in the square are right, that means that every vertex of a square can actually play the role of the vertex of a circumference angle from which the corresponding line segments formed by the given points, for example, a line segment AD and a line segment BC, is seen under right angle, and such A circle can always be constructed with Euclidean tools alone. All we have to do over here is construct the corresponding line segments AD and BC and cut these line segments in half with the perpendicular bisectors BAD and BBC. And once that happens, what do we observe? Let's say we name this perpendicular bisector the perpendicular bisector AD because it cuts the line segment AD in half, and this blue line will be perpendicular bisector BC because it cuts the line segment BC in half. Again, here, just like in the previous segment, we assume that the points A and C lie on the opposite sides. This is our assumption. The point A and the point C lie on the opposite sides or the extensions thereof. Now, I will not be as thorough as I was in the previous case, but here we will see again, we will generate two distinct squares in general per one assumptions that if we fix the point A, we'll take the point C lying on the side that is opposite or extension thereof, then the point B, then the point D. Now, once we construct these helper circles, the helper circle SD that has the point E, the midpoint of the line segment AD, as the center and evidently the length EA or ED as the radius, and the circle, where is it, SBC, the shown in blue, that has the point F, the midpoint of the line segment BC as the center, and the radius FBFC taken as their distance. Then as our solution steps, I already outline our solution algorithm. This is what we do. The helper, let's call them the auxiliary circles. We construct them as shown, the green and the blue. Then as the byproduct of constructing these circles, we will obviously construct the perpendicular bisector BBC and BAD, the green line here, the blue line here, in order to obtain precisely the points that are equidistant from the extremities of these two triangles. Now let's look at the interesting property of these perpendicular bisectors and the diagonal of the parent or mystery square shown over here in red. That diagonal will cut the interior angles of our square exactly in half. 90-degree angle, 90-degree angle, but the red line that connects the vertices unknown to us, yes, vertices P and R of the mystery square exactly in half. 45, 45, 45, 45 degrees. Again, it goes without saying that in the previous case we worked in reverse order, and in this case we also work in reverse order by assuming that somehow the given square was magically reconstructed, and now we're trying to extract information that is useful to us or analyze the problem in the solved state in such a way that we gain insights into how we can generate the solution in the forward flow of causality order, which is sought after. And here is what we observe. Again, two helper circles. As a byproduct of these two circles, we'll have two perpendicular bisectors, and we will see that these perpendicular bisectors will intersect our auxiliary circles at two distinct, again, diametrically opposite points as marked, H and H prime, G and G prime for the green circle, for the blue circle. But here is the interesting thing, precisely because every diagonal in every non-degenerate planar Euclidean square is a bisector of the corresponding interior angle. That means that the angle, for example, ARG will be what? 45 degrees, and the angle DRG will be 45 degrees. Likewise, the angles HPC and HPB, this is the point B right here, will be 45 angles. But remember, in Euclid's Elements, this theorem goes under Book 3, Proposition 26. Equal angles stand on equal arcs, whether these angles are in the circumference or central angles. That means that if we take the angle, the circumference angle DRG, then the corresponding central angle will be AEG. And if this angle is 45 degrees, then this angle must be what? Necessarily 90 degrees. Likewise, if we take the angle DRG, the corresponding central angle, this angle in the circumference, the corresponding central angle DEG will be what? Will be also twice the magnitude of the angle in the circumference. 45 times 2 is 90, so 90, 90, 90, 180. And what does that mean? That means a very interesting observation is about to happen. It means that the point, our first point, G, let's say, which we mark over here, G, and its body, the point H on the blue auxiliary circle, will cut the corresponding arc AD on this way. What? In exactly half. How else can it be if we have 90-degree and a 90-degree angle? And these arcs must be equal length, again, by the same theorem, Euclid's Elements, Book 3, Proposition 26. But that means that even though we cannot construct in the forward flow of causality solution, we do not know what the points P and R and what the corresponding diagonal is, but because this point, you see, it plays two roles. It's sort of overloaded. Its function or its location overloaded. It can be recovered in two distinct ways. One way is by snapping a diagonal, but that's if the square is available. But in our case, when the square is not available, the line segment AD is available and its perpendicular bisector BAD is available. As such, if we snap the perpendicular bisector of the line segment AD, this perpendicular bisector will intersect our auxiliary or helper green circle at two distinct points, G and G prime. Right now we concentrate on the point G, and that point G will cut the arc AD exactly in half. In other words, through that point G, there must pass the diagonal that emanates from the corresponding side. Likewise, here our perpendicular bisector BC will cut our circle, helper auxiliary circle SBC at a point H. That will also be the point through which the same diagonal, the same exact diagonal that passes through the point G will pass. As such, here is our solution. Look at this. First, from the points G, G prime, H, H prime, we take these 2 points, and algebraically it's very easy to put them in the circle and say go. The algebra of our algorithm corresponds to which geometry? It corresponds to the following geometry. We pick the points at which our perpendicular bisectors intersect our auxiliary circles in such a way that they face each other, so that they face each other, or they are, let's say, closer to each other than their opponents, the points H prime and G prime. As you already understand, in the next segment, in a few seconds, I'll show you how to construct the corresponding square when we take the points G prime and H prime as our generating points that will generate a solution square. But here we'll concentrate on this points G and H, which face each other. In other words, G and H are on the arcs that are closer to each other, or in some sense belong to the innards, if you will, of the points A, B, C, and D. And now we have it that the straight line GH, which we can always construct because, again, line segment as a diameter, perpendicular bisector, circle, point G, same thing over here for the second pair of points, BC as a diameter, perpendicular bisector, circle. The perpendicular bisectors will cut the circle at two distinct diametrically opposite points. We pick the points that are facing each other, and through these points we construct a straight line that now will, at intersection, look over here, with the corresponding circles generate the missing, so to speak, the missing vertices of the mystery or set after solution square number 1, the point R. So our straight line GH will intersect the auxiliary helper or helper green circle SAD at the point R for the second time. For the first time, of course, it will be the point G, and likewise that straight line GH will intersect our blue auxiliary circle for the second time at the point P. at the point P, at the point R, and this is it, game over. We now know the locations of two vertices of the mystery square and the locations of all points. At this point, this is a no-brainer. Straight line BP, straight line CP, straight line RD, straight line RA, straight line BP, once we know the location of this point, straight line CP, because we know the location of the point P. Likewise, over here, straight line RD and the straight line RA. Boom, problem solved. One solution square is constructed. And now let's take a look what will happen if we apply the same logic, but this time we pick the points where our perpendicular bisector of the line segments AD and BC intersect circles at the points that specifically do not face each other. As such, when we pick the points where the perpendicular bisectors of our helper straight line segments A, D, and B, C intersect the helper circles at the points that do not face each other, we refer to these points as G prime, and H prime, We essentially do the same thing. Instead of snapping the straight line GH, we snap the straight lines G prime, H prime. Again, you can pull the same trick. The algebraic structure of our algorithm number 2 is exactly the same, and the mathematically inclined thinkers in our audience should have no problem with basically canceling the points G and H temporarily and letting the points H prime and G prime play the role of the points G and H in the previous solution. In other words, we snap a straight line shown in red. Hopefully you can see it in red. G prime, H prime. This straight line will intersect our helper circles at different points. R prime, where our original, let's say, vertex R of the mystery square moved to this point, and that straight line will intersect the blue helper circle at the point P prime, but the idea is the same. Remember that the straight line G prime, H prime, just like the straight line GH must house what? It must house the diagonal of the mystery square. And in our case, that diagonal is shown over here, this little bit right here. But the idea is that the angles at the vertices R prime and P prime are what? They are right by the Thales' theorem. In other words, in the previous step, we had the angle ARD right over here. But now we have the angle AR prime D right over here. Again, I probably can carefully insert the right angle designation here and the right angle designation here. Likewise, in the previous solution, the angle BPC was right. But now it's essentially the same angle, but now the point P moved to the other side. P prime, the angle BP prime C is right. Game over. We construct our square, the second solution square, distinct by using the same ideas, but this time instead of picking the points P and R, we replace them with P prime and R prime. So we draw a straight line B P prime, we draw a straight line C P prime, and we do the same for R prime, A R prime and D R prime. These four straight lines will intersect in such a way that inside they will trap a square. This will be the second solution square. It's, let's say I'll cross hatch it. I don't know, maybe I'm making things more messier than I should, but hopefully you can see that the smaller red solution circle is the second distinct solution. Again, in general, taking all the favorable mutual juxtaposition of the material that we're given, tilting it to our side. But this is again based on the assumption that the points A and C still belong to the opposite sides of the square. And in the second solution square, what happens? Well, the points A and C, they technically do not belong to the same sides, but they belong to the extensions of the opposite. I'm sorry, they do not belong to the opposite sides, but they belong to the extensions of the opposite sides. And that is the case, in order to help you visualize what is going on with the second solution square, I put together another small demonstration where I will again wiggle the points A, B, C, and D so that you can see how the second solution or second distinct circle shown in red over here behaves. Now that you saw the animation or the demonstration in action and you have a better feel for how the second distinct solution square behaves, if we construct our two distinct solution squares based on the assumption that the points A and C belong to the opposite sides of the mystery square or the extensions thereof, then you should again see that under the next two assumptions, the points A and B, A and B, and the points A and D belong to the opposite sides. And again, in the best case scenarios, two solutions per assumption for a total of what? The grand total. 3 times 2, again, 6 solutions in general, which agrees with the previously obtained results. And we can move on to the solution number 3. Our third solution of the mathematical problem S3E17 is based on the combination of two geometric transformations, rotation and parallel translation, and that solution is a variation on the theme of orthogonal intersecting chords theorem that we proved early on in this episode. And the idea here is the following. Again, we solve this problem in reverse order, assuming that the problem has been solved somehow. The sought after square was reconstructed, and let's say we can reason with respect to literally any other point, because I started working with the points A and C. I'll keep working with them, but you can work with any other points. The idea here is the following. Rotation. What do we rotate about what, by how much, and in which plane? The rotation is evidently in the parent plane. We rotate the point A about the point C by 90 degrees, let's say in this particular case clockwise, because why not? Under this rotation, the point A will be taken into the point A prime such that the length of the line segment CA prime will be equal. The length of the line segment, where should I write it? CA prime is equal to the length of the line segment CA, because rotation is a rigid motion. It preserves the distance between any 2 points, such as C and A. So the length of the line segment CA prime is the same as the length of the line segment CA. And now what do? We translate the line segment CA prime, this line segment over here, along the vector CD. Along the vector CD. C is given, D is given. In high tongue, the vector can be constructed, so the line segment CA prime is translated along the vector, or in other words, we put the point C into the point D under this parallel translation. And what happens to the point A prime? Think on your feet. Yes, the point A prime will be taken by this transformation into the point Z, such that the point Z will belong precisely to the side of the mystery square, in this case PQ, but in this the names of the vertices are irrelevant. What is relevant is that under this translation, the line segment DZ will be what? It will remain perpendicular to our original AC, and these line segments DZ and AC represent what? Exactly, they represent orthogonal intersecting chords in our mystery square. In other words, the length AC must be equal to the length DZ. And because D rests on the side of the square, the chords are orthogonal, and AC, all the points AC belong to the sides of the square. The point D belongs to the side of the square. The point Z has no choice but to belong to the corresponding side of the mystery square. And once we know that location, the location of the point Z, game over. Straight line ZB marks one side of the mystery square. Straight line through A perpendicular to ZB one side. Straight line through the point C perpendicular to ZB the other one. And once we have these two straight lines through D perpendicular to either this one or this one, the intersection of these four straight lines marks the square. Again, make sure that you understand why the orthogonal intersecting chords theorem that we proved earlier. And that brings us to the algorithm as follows. First, we draw the straight line AC. Then we draw the straight line lowercase PAC orthogonal to AC through C. This is this straight line right here, PAC. Then we snap a circle S that has the point C as its center and CA as its radius. This circle will intersect our perpendicular straight line PAC again at two distinct points, A prime and A prime prime. The point A prime is shown over here. The point A prime prime lives somewhere at the bottom of the screen. You cannot see it, but you should analyze it. That's the second solution square. And once we have the location of the point A prime, then we draw the straight line CD. We can do that with a straight edge. These points are given to us. Then as a step number 4, we draw the straight line. I call it A prime Z for the lack of the better name, because I don't want to throw too many names. But the idea is what? A straight line through the point A prime parallel to CD. This is the primitive task that is constructible with Euclidean tools alone. So we have two straight lines parallel to each other, CD and this straight line, the blue one, let's say CZ. And then as the last step, we draw the straight line P, lowercase pd, orthogonal to AC. Orthogonal to AC is this straight line right here that passes through the point D, this one, P uppercase D. See, is orthogonal to AC. And that straight line will intersect perpendicular to AC through D, but this straight line will intersect our previous parallel constructed here precisely at the point Z. You see, these are the steps in order to nail the location of the point Z. Once the location of the point Z is known, the reconstruction of the square based on the given points becomes trivial, as I explained. And now we can move on to the solution number 4. The fourth and the final solution that I can think of for the mathematical problem S3E17 is based on the following idea. The midpoints of the chords of our square belong to the axis of symmetry of that square. And the idea here is following. Let us say we are given again the points A, B, C, and D. I split these points for your convenience, and let's say again we go by the same assumption. The point A and the point C are on the opposite sides or the extensions thereof. What is the claim over here? The claim here is the following. The midpoint of the line segment AC, or the midpoint of the chord of our square AC, I call that point MAC, shown in blue over here, such that the line segment MACA is the same length as the line segment MACC. That point MAC belongs to the, in this case, let's say logically vertical axis of symmetry, which means that the horizontal displacement of that point with respect to the sides of the square that house the points that are the extremities of this chord is exactly the same. So in other words, in this case, this line segment over here and this line segment are the same. How do we prove it? The proof is trivial. It's sub-baby proof. We draw through the midpoint MAC, we draw a perpendicular to both of these sides, and we have two smaller triangles. The angles at the point MAC are vertical. These angles are right by construction. The remaining angles must be equal. So by angle, side angle, and angle, side angle, these triangles are congruent, and because precisely the blue line segment is perpendicular to the sides of the parent square, that means that these distances are not only they're the same, but they are exactly 1/2 of the length of the side of our square. I showed over here the blue line segment A/2. These line segments are 1/2 of the length of the side of the square, and that means precisely that the point MAC sits somewhere. It doesn't have to be here, unfortunately, because the drawing is small. It looks like MC, the point MC, the midpoint, sits in the middle of the square. Is not the case. If we really shift somehow the chord AC, then the point MC will travel along this vertical axis of symmetry of the square, but it will not be in the middle. It will be somewhere here or whatever. And I depicted this position over here. Likewise, if we take the other two points B and D and form a chord with it, then again the midpoint MBD over here shown in the middle, such that the distance MBD to B and MBD to D is the same. In other words, this red distances are the same. The claim here is that this midpoint MBD is displaced vertically from the corresponding sides that house the points which form the chord by the same amount. And thus that point belongs to the horizontal, logically horizontal axis of symmetry of that square. Again, how do we prove it? Through the midpoint MBD, we snap a perpendicular to the sides that house the points which form that chord. And the smaller triangles, again, by what? Angle, side angle, vertical angles, and then side. These triangles are congruent. It means that in congruent triangles against angles of the same magnitude lie the sides of the same length. So here the green line segments over here, this one and this one, must be the same. And not only that, because this line segment is perpendicular to the sides, it means the n is cut in half. That means precisely that these two line segments are equal in length. This proof is trivial. I captured this over here, these green line segments A/2, so they are equal. In other words, we have it that in the case of the first chord, we have this displacement of the midpoint, which by magnitude again, or by length, if you will, the same as this horizontal displacement of the midpoint that cuts the other chord in half. And that observation motivates the solution number 4. And here is the idea. You can think on your own, but my idea is the following. We rotate the point C about the midpoint MAC, rotate the point C about the midpoint MAC by 90 degrees counterclockwise. We rotate this point like so, this way, by 90 degrees. So we are setting up, what are we setting up? We're setting up the orthogonal intersecting chords theorem to bring it in action over here. Once this rotation is made by 90 degrees, let's say we rotate our vertical axis of symmetry also by 90 degrees. By doing so, this vertical axis of symmetry, it will not be taken in general into the horizontal axis of symmetry, but it will be taken into a straight line V prime that will be parallel. You see, this blue line V prime will be parallel because of the 90-degree rotation. That straight line V prime will be parallel to the genuine horizontal axis of symmetry of a square. But again, in general, there will be some delta, there will be some distance between them. But precisely because these blue line segments in some sense will also be rotated vertically like this, it will be displaced from the top like this. So the idea is the translation upward will put our point C prime precisely on the side. So that is the idea, is that, look at this. One small blue line segment rotated by 90 degrees will be vertical, but it will be displaced. But the distance, the length of this line segment is the same as the length of the green line segment. And the green line segment lands dead on the side of our square. So the idea is that by parallel translating that little segment by this delta, by the difference between the v prime and h, between the horizontal axis of symmetry and v prime, which is the image of the vertical axis of symmetry under the 90-degree rotation, we will precisely land our point. The idea is to land the point C prime, which is the image of the point C under the 90-degree rotation, counterclockwise in the parent plane, on this side and on the side of the mystery square. We call that point Z. And once the location of the point Z is known, that's it, game over. You already know how to do a 4-point square reconstruction, straight line through one point that's given over here, perpendicular, perpendicular, and then perpendicular, game over. But in some sense, if we capitalize on the fact that the blue line segment has the same length as the green one, we can shift this line segment vertically up. But in terms of Euclidean tools, I'm thinking, I did not carry out all the arithmetic myself. Maybe this algorithm actually will be shorter, maybe not. It feels like it should be it should cost us more steps, but maybe I'm wrong here. Keep me honest. So what we can do, we can capitalize on the constructions that we already carried out and use the points that we do have. We do locate in the upcoming algorithm, that's what we will do. Connect A and C, cut it in half, connect B and D, cut it in half. We have the point MBD. I will refer to these points as E and F, so they're not as clumsy here. They're descriptive, but it takes a lot to describe them. So here I'll call these points, midpoints E and F. Once we have these points, we will translate this line segment, 1/2. We will translate 1/2 of our chord, of the first chord, by the vector MA that connects the middles, MAC and MBD, through this vector, you see. And once we translate this vector, boom, it will put the point C prime exactly on the into the point Z that must belong to the corresponding side of the parent mystery square. And why is that? Well, because again, remember, rotation is a rigid motion. This length equals this one, but this is 1/2. Once we put it on, the length will be the same, and that translated line segment will be what? It will be orthogonal to the original one, and boom, we have our orthogonal intersecting chords theorem in action. So once you understand the idea behind and the motivation behind this algorithm, here is how we implement it in practice. The actual Euclidean tools only algorithm for my solution number 4 is simpler or more straightforward than the explanation. The explanation probably sounded more scarier than it is, but when we translate it into the straight edge and compass steps, these steps become very, very simple as such. First, we construct our two chords AC and BD. We construct our chords AC and BD, and we cut those in half with the points E and F. Here I wrote down the step number 2, perpendicular bisector AC, perpendicular to the chord AC such that the length of the line segment AE is the same as the length of the line segment EC. This is the blue point E. This line segment is the same as this line segment. Likewise with the perpendicular bisector BD, which runs perpendicular to the chord BD and cuts it in half in such a way that BF equals FB. This is the green point F shown over here. We have it. Then, as the step number 4, we construct a perpendicular FBF perpendicular to AC, but through the point F. We pay attention here, through the point F. In other words, we cut both chords in half, but then through the point F, we construct a perpendicular to AC. So this is our AC. Perpendicular to it runs through F. Pay attention here, not through E, but through F. See, this is our parallel translation. In a sense, this is our parallel translation. I do not want to pollute the drawing more than I have to. These things are quite messy as it is, but you understand the equivalent of this translation of the line segment EC will be along the vector EF. And that's it. On the step number 5, we construct the circle that has the point F as its center, and we pay attention here, the length of the line segment EC as its radius right here. This guy as its radius. See, we bring it down here. That's it, the point, and we call that circle S. Shown in blue, we call that circle S. I showed one arc over here, there will be another one. I do not want, again, to make it more messier, the diagram more messier than I have to, but our circle S will intersect the perpendicular PF constructed on the step number 4 over two distinct diametrically opposite points, Z and Z prime, point Z prime, Z prime, and the game is over. Once we know the location of the point Z, the rest is just a smooth sailing and a home run. Straight line ZB right here, and then LA perpendicular to ZB through A. This is the yellow line right here. LC perpendicular to ZB through C. The yellow straight line right here. LC, LA, LC. Once we have these two straight lines and this one, we snap a straight line through D, through the fourth point D, that is perpendicular either to LA or LC. Game over, and this is it. Now, like I said before, this problem may or may not have anything to do with Sofya Kovalevskaya, as I said before. Maybe it is true, maybe it is not, I do not know. But regardless of its ownership, this problem definitely belongs to the great international mathematical Grape wine number 1. Number 2, it is an amazing problem. You just saw 4 distinct enough solutions, and if you have any other solutions of this problem that is distinct from the ones that we presented in this episode, I would like to hear from you. Even though, again, I have to admit that every time we develop a new solution, or we think we develop a new solution for the existing problem, it becomes more and more challenging to actually verify and prove that the solution that we just offered is indeed distinct from all the previous solutions generated so far. And to be honest with you, here, as I look at the solution number 4, I'm not really that convinced that this solution is indeed that much distinct from the solution number 3. Both times we make rotation, we make parallel translation. Tell me what you guys think about it. Do you think the solution number 3 and the solution number 4 are really distinct? But I think they are fairly distinct precisely because the motivation is quite different. Remember, in the solution number 3, we rotated 1 point. What did we rotate? We rotated A about C. Here we rotate the point C about the midpoint. So the reasoning is quite different, and I think because mathematics is an art of telling a story, and that story is the most important, the consequence of it is, of course, interesting and maybe deep and influential, but it is the story, or a story from A to B, from the problem to a solution, is where the gold is. So as far as I'm concerned, if the stories or the motivations for solutions are distinct enough or different enough, then the corresponding steps, even if they look similar, they should be distinct as well. Now, this is it for the mathematical problem S3E17, and we will move on to a new challenge next. Our next challenge will be the problem in physics, S3P4. This problem is quite straightforward. There's very little physics in it, but it can be used to test your mathematical prowess. And back in my time, it was a perfect candidate for real-time, face-to-face verbal physics examination as a conversation starter. And you're expected to solve this problem in about 5 minutes or less. And the setup in this problem is the following. This is a kinematics problem where we're given a point P that executes the motion over a horns-up parabola shown in blue. Y equals kx squared, where k is a strictly positive real number that is known and given ahead of time in the traditional orthogonal coordinate system x, O, y. The angle over here is evidently right. There should be a unit of scale on both sides, but let's pretend that this unit is known, and I will not pollute the graph. But the condition here is the following. The point P executes the motion over the horns up parabola y equals kx squared as its equation in the x or y coordinate system in such a way that its acceleration A as a vector is always parallel to the y axis. In other words, the point P moves in such a way that its acceleration A is parallel to the y-axis. It remains like so at all times as the point moves along the parabola, like I said. And we take it that the real numbers k and a are given ahead of time. They are known, and the objective is you are to find the normal acceleration and the tangential acceleration as the functions of time. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the physics problem S3P4.